And I'm still paying you. I got the hard ass beats like the crack of the tech. Still paying you. Think y'all forgot what rap sounded like? I'm still paying you. Back to match up beats, the bang of the average. Still paying you. I'ma make y'all pay for the dues.
All right, give it up for DJ Cash. You look swell.
Thank you, thank you.
Why?
Just coming back from court, trying to get back payments on my royalties.
Court?
Yeah.
Did you win or you don't know yet?
I'm not too sure. I'll let you know next week.
Okay. There's a lot of announcements. Actually, announcing for you as well. You have a radio show starting this week.
I do, on Sunday.
This Sunday.
From 1 to 2 p.m. I have a show starting from WRCT. You guys should all lock in.
All right. This Sunday, DJ Cash is on the radio. Are they paying you or no?
No.
All right, you got to work on that. Okay. For you guys in the class, homework 2 is going to go out today. That'll be on the 21st. Project 1 got released yesterday, and that's going to be due on September 29th. Has anybody looked at Project 1 yet? Any questions about Project 1? So we'll announce the recitation. That'll be next week. But all the files and everything should be on GitHub. So pull down the latest version and make sure you're working off that code base. And then, as I said, last class, next Monday and Tuesday on the 16th and 17th, we are having our industry affiliates visit day. So a bunch of database friends from various companies are coming to campus to give talks and meet with you guys. So 15th will be research talks and poster sessions with students and other researchers at CMU. And then on the 16th in the morning before like 12:30, there'll be 3 sessions of different talks from the companies. You can talk to them about internships and full-time positions. And like I said, we'll send them your resumes if you fill out the spreadsheet that I posted on Piazza. Okay? Yes, question. The question is a list of research talks and times? Yes, that link, in the slides, that link will take you to the page. We don't have the finalized schedule is not ready yet, but that'll be posted probably tomorrow. And then for the company sessions, once everyone fills out the form tomorrow, we'll figure out what the actual optimal ordering will be. Okay? Any other questions? All right. So this is very unusual, but there was very, very, very huge news today in databases like 2 hours ago. Anybody know what it is? Like groundbreaking news, like the biggest news story in your lifetime. Nobody. Larry Ellison, the founder of Oracle, is now officially the richest person in the world. He dethroned Elon Musk. What's that? Well, who? I don't know. He doesn't do databases, right? This guy does, right? All right. Larry Ellison is like the OG of database money, right? Now he's the richest person in the world. It's all paid for by databases. He owns a Hawaiian island, paid for by databases, and like a big one, right? Not the one that had all the lepers, right? One you could actually see from like Maui. He bought his son from his 4th marriage. He bought his son from his 4th marriage, a movie studio, right? He got married last year to the woman, she's 36, he's 80, whatever. Like, that's his thing, right? This is a big deal. Like, I know he's worked so hard for it, and it really means a lot to him. And I sent an email congratulating him. But this is it. This is why we do databases. This right here, right? So, I mean, I would do a round of applause for him, but he's not here, so that'd be kind of weird. But this, again, he's been bumping back and forth between 5th and 7th, and then earlier in the year, he went to 3rd to 2nd. So this is a big deal. And I get emotional, but this means a lot. Okay. All right. So we're not there yet. We're not at Larry's level, but we'll get there. All right. So last class, we spent time talking about the buffer manager, right? We said that this was this component inside of every database system. If you're not using mmap, you shouldn't be, right? If you're going to manage your own memory in your database system, it's the component that is responsible for storing database pages from disk into memory, handing off pointers out to other parts of the system, keeping track of like the reference count or whether they're dirty or not, right? So doing all the the machinery that allows us to have the illusion that our databases actually can fit memory, even though it may not, right? So today's class, I want to quickly go over some 3 optimizations we missed at the end of last class. Then we're going to jump back now to the disk level and refresh your memory about what tuple-oriented storage looks like. And then we're going to look at 2 alternative methods, index-oriented storage and log structure storage. And then at the end of class today, we'll finish up with a talk from the SingleStore guys. All right, which actually is not a disk, or these started off not as a disk-oriented database, was an in-memory database, where the primary storage location of the database was the in-memory. They've since switched that, but it's a pretty state-of-the-art system. And the founder of SingleStore was actually the founder of Neon as well, who got bought by Databricks for $1 billion last year. So again, Larry Ellison's not the only one who makes a lot of money in databases. Okay. So last class again, we were trying to quickly go over the buffer stuff at the end, or the disk scheduling stuff. And I want to come back and talk about buffer optimizations. Again, these are going to be examples of things your data system can do because it has full control of the memory and what's being read and written from disk. Again, these are things that the operating system is not going to be able to do very easily because it doesn't know what queries are running and what the queries want to do. But we, as the data system, we know, right? Because SQL is declarative, we know what the query plan is going to look like. Therefore, there's a bunch of tricks we can do to make things better. So the first one is maintain multiple buffer pools. So I talked about this buffer pool being like this region of memory, and we're going to put our database pages in there. It doesn't have to be logically organized as a single block of memory. We actually could break it up into sort of sub-arrays and have a page table per subarray and have different policies and algorithms used to optimize those different buffer pools. Right? So you can have one for database, one for table. You can have one per like page type. If it's going to be indexes versus table pages, you split those up, right? And so the benefit again I'm going to get is that because now we can tailor the buffer pool's internal algorithms based on how we know the rest of the system wants to use the data that's going to put in that buffer pool, we can make better decisions about what to evict and when to evict. And we're actually going to reduce latch contention when we have multiple workers trying to access the same data structures at the same time, because now things are split across. So this is something you'll see in the high-end systems, the enterprise systems. Like in DB2, you can go crazy, like not from IBM system. Like you can declare a buffer pool per table, per index, per blob type. Like you do a lot of very sophisticated things. MySQL has a pretty simple one. We'll see that in a second. So there's basic 2 ways to do this. You can just say, all right, well, if I have since I know I got to do lookups on record IDs or object IDs, like the object could be like a table or an index, then when I do my lookup to try to get that page that this object belongs to, I'm showing some arbitrary command, get record, whatever. Like it's not really SQL, obviously. But you could pick apart this record ID, look at maybe the first portion of it, that's the object ID, and use that to decide which of these different buffer pools are going to have the data that you want. And the thing about the guarantee, if we have multiple buffer pools, is that any page that we want, any like a physical page, can only exist in only one and only one buffer pool at a time. Right? You don't want to have 2 copies because then if you do 2 writes, how do you keep those in sync? Right? We don't want to do that. Right? So again, with the simple mapping, we can just say, okay, this is what we want for this object ID, and we know it's in buffer pool 1, and go get it over there. Another simple trick, and this is what MySQL does, is that you could just take whatever the record ID is that you're trying to find. Like I want page 123 or record 123. Just hash it and modify the number of buffer pools that you allocate at the beginning, and then mod it by that, and it just tells you where to go find it. Again, this has the same property guarantee that any page that we're looking for can only be in one of these buffer pools at a time. Right? I'm showing 2 buffer pools. You could have hundreds. Right? And then there's a disk scheduler underneath to make sure that if you're trying to, all these buffer pools instances are trying to read and write data at the same time. You don't want to do random, have a bunch of random I/O. The disk scheduler can see all the requests and then sort things and try to do it in a more efficient manner. Another trick we can do is prefetching. So again, we haven't really talked about what query plans look like. Just assume that it's the program that we know we're going to execute in order to run some query. Right? So we know everything ahead of time what's going to happen. So if we see a scan occurring on data, right, so query 1 is going to start. First thing it needs is page 0. And then it starts reading page 1 and go read that. But if we recognize that we have this sequential access pattern, then the database system can say, okay, well, you just read page 0 and you read page 1. I know your query is also going to need page 2 and page 3. So let me go ahead and prefetch that for you, put that in the buffer pool while you're crunching on page 1, right? Run whatever eviction policy that we want to run, put those pages in there. So then now when the query says, all right, I'm done with page 1, let me go look at page 2, it doesn't stall and wait while you're going fetching from disk. The data you need is already there, right? And you do that for the rest of the pages all the way down. Now, Mmap can do that, actually. The OS can do this, right? OS has a way to do, you can pass hints to say, I want to prefetch as I'm reading a file. But it can only prefetch sequentially, right? It can't do anything more sophisticated because it doesn't know what's in these pages, doesn't know how they're related to each other. So you can do tricks like this. So say I have a query, wants to get data within a range. And the data system decides, okay, well, I have an index for this. I can use that to find the data that I want, right? Assuming some tree data structure. It's most likely going to be a B+ tree. We'll cover that in a few weeks, but it doesn't have to be, right? And along the leaf nodes, the data is going to be sorted in that key order we want. So now as my query starts running, I read index page 0, that's the root. That's going to tell me what I want to go left and right. Now I go down here, I go to page 1, I fetch that in, and that just had to be sequential in my database file. So yeah, you could potentially prefetch that. But when I get down here to the bottom, I can see that I'm going to scan across the leaf nodes, and I know I'm going to need page 3 and page 5, and they're not sequential. So if the OS was doing this for us, it would blindly say, okay, well, you just read page 2, page 1, page 2. Let me go get page 3 for you, and 3 and 4. But we actually want 3 and 5. But because we know the contents of these pages, we can peek ahead. And we'll talk about in a few weeks how we do that. Say, oh, we don't actually want 4. We actually want 5 because we're scanning along the leaf nodes. And we go ahead and prefetch those guys. Right? So again, this is an example. Because the data system knows what you're trying to do, the queries, it's in a better position to make decisions about how to optimize things. All right, the last one I'm talking about is scan sharing. And the idea here is that if we have a query that's running and it's scanning some table, and then some other query comes along and wants to scan the same table, rather than just having that second query start from the beginning and just read all the same pages that the first guy just read, we actually can piggyback and ride along the first query, see all the pages that it sees, and then make a determination whether we want to quit or not, or come back around and find the data that we're looking for. These are sometimes called synchronized scans. And again, this is done at the lowest level of the system as there's some cursor reading pages from page directory or scanning along a table. This is not the same as result caching. Result caching is like I take a query, I run a query, I produce some output. If that same query shows up, I just reuse the same output. This is actually done at the lowest level, actually, while we're running queries. So this is actually rare. Not few systems support this. Again, the high-end ones like DB2, SQL Server, Teradata, and Postgres do this. Postgres is the exception. Oracle, again, despite him now being the richest person in the world, doesn't have this feature. They have something that almost looks like this, but it has this limitation where the queries have to be exactly the same in order to do this piggyback mechanism. Right? So meaning, this is from the documentation. If you have a query like select star for employees, if the next query comes along, it says select star for employees with the capital E, all right, or there's an extra space in there, it doesn't match it. Even though semantically they're the same, the way they're doing this matching is basically hashing the string and seeing whether it's identical. Right? But high-level idea is still the same. All right, so say we have this query, select the sum from A. It starts at the beginning. It's going to scan through and read all the pages that it needs. And then say at this point we get here, we need to read page 3. We only have 3 frames in our buffer pool, so we're going to throw out page 0. And then while we're doing this now, another query shows up that basically wants to do another sequential scan on the entire table, but now compute a different aggregation. So the computation is different, but the data it needs to access is the same. So we could do the stupid thing and just start this second query from the very beginning of the table, but it's going to read page 0, and that's actually the last page we just evicted. So we just go back and now fetch it back in our buffer pool. But if we're smart about it, we can say, okay, well, these are both doing a sequential scan on A, so I'll just have Q2 tag along Q1. As the cursor reads the table and gets all of these pages, it can do whatever computation it wants. Then at the bottom, Q1 says, oh, I scanned the entire table. It goes away. But Q2 says, well, I know I started at the beginning, the sort of halfway point of this table, and there's a bunch of more pages I need to go back and read. So let me start and scan through those all over again. Right? Again, we talked about this in last class. Like, we want to maximize the amount of computational work we can do on data pages when we bring them from disk into memory. So if I can run 2 queries or satisfy 2 queries operations for one single page fetch, that's a huge win for us. Yes?
Is there a way for like query 2 to know that? Like go back before they start sharing?
Like here.
At this point, query 2 hasn't seen page 1 or page 2 yet, right?
Question is, question is, at this point here, query 1 has not seen page 1 or 2.
Query 1 has.
Yes, but
query 2 needs to see page 1 and 2
yeah,
in memory.
yes.
Instead of starting with query 1, reading 3, 4, 5, could it read 1, 2 first?
Yeah. So his statement here is could be more sophisticated and have Q2 recognize I need page 1 and 2. That's already in memory by going peek in the buffer pool, and then say, okay, let me read those and then piggyback. Yes. In this PowerPoint example, I'm not showing that, but yes, that you could do that. Now, who does that? I don't think Postgres does. I don't know what the enterprise guys are closed source, so I don't know what they do. Yes.
How do you know what pages correspond to what table?
The question is, how do you know what pages correspond to what table? The page directory tells us. Yeah, page directory is basically a catalog and says, okay, if I want to read table A, here's the directory, or here's the pages, the file with here's the directory with the files that have the pages that you want to read this. Yeah, we have to know that. The statement is, this is a sequential scan. If it was an index scan, it might not do the same, read the same pages. Yes, if there's a predicate there from A, from A where something, you might not want to read everything. If it's an index, sure. Keep it simple, sequential scan. Right? All right. All right, so again, that's the 3 optimizations I wanted to cover in the buffer pool. So let's jump back now and talk about the disk storage again, the database storage on disk. So we said at the beginning of the semester that again, we're going to focus on what I'll call a disk-oriented architecture. Again, we assume that the primary location of the database when it is at rest is on non-volatile storage like a disk. And then we talked about a way to break up a database, it's the entire database into these database pages, and represent them in as slotted pages where we could stick in tuples and then do lookups later on. Right, so we discussed the page layout. So that page layout would be, again, what are actually in the pages. So what's in the pages that we're storing in our database files, right? And we talk again, tuple-oriented storage. That was the slotted page architecture, where the pages are really all about storing tuples, and we have this indirection layer within each page that allows us to move data or tuples around within a single page itself. So today I want to now look at 2 alternatives. Again, we'll refresh what a tuple-oriented storage looks like, but then we'll jump into the new stuff for today. All right, and these are going to be alternative ways to store data for tables in a database. So again, slotted page. I said this is the most common layout for databases that are row-oriented. Next class we'll discuss what that means in more detail. Basically, we're going to take any tuple, and assuming we can fit it into this page, and we're going to store it from beginning to end inside that page. And then inside that page, we have this header that tells us some metadata about what's in the page, like a checksum, a version number, so forth. Then there'll be a slot array at the beginning that and all the tuple data at the bottom. And the slot array is going to have basically just record offsets inside the page that tells us where to jump to find the beginning point for every single tuple. And we said the slot array is allowed to grow from the beginning to the end, and the tuple data is going to grow from the end to the beginning. This is the way Postgres does this. This is the way I think the textbook might describe this. Other textbooks might reverse it. In the end, it doesn't matter whether the slot array or the tuple data is on the top or the bottom. The high-level idea is the same, right? And again, and the slot array is providing us an indirection that allows us to change the position of tuples within the page itself, right? We don't want to move it to another page because we may have to, but that's not we're not focusing on that yet. And this allows us to then be able to do things like, oh, I'll delete this tuple here, and then I can do compaction and slide this tuple over here to fill in the space, right? And all I have to do now is update the slot array to tell me where the offset is for that tuple I just moved, and I don't have to update anything else outside the system or outside this page itself. Then we talked about record IDs, and this was the way that we were going to physically find a tuple within our database. Right? It's gonna be some combination of like a file name or file ID, a page ID, and then a slot number within that page. Right? So the page directory thing he was asking about before, they were asking about before, that'll store the file ID for some object. Like if I want table foo, here's the file where to go find it. And then if I want page 123, depending on the addressing scheme the data system uses, it could just be an offset within the file, or it could just be the file name itself might have the page number, right? All that's within the page directory. Yes.
What if you have like more rows than you have the size of the ID?
The question is, what if you have more rows than the size of the ID? I mean, it's a 64-bit number. Well, hold up. In Oracle, it's a 10-byte number, right? That's pretty big.
Well, in the Ingress, it's
So Ingress is what the first relational system from like 1974. Postgres is, yeah, so 6 bytes. Statement is, would you run out of 6 bytes? I mean, it's a pretty big, that'd be a pretty big table.
Yeah.
But in theory, yes, you could. There's other limitations too, right? So like, the statement is, it's not just for one table, it's for the whole database. Now, this would be for, depending on the scheme you're using, this could be for the entire database. It could be for a single table, right? I know I want table foo, and here's the page ID for it. Therefore, I know how to find that, right? There's other limitations we're not going to talk about. Like in Postgres, you can only have 2 to the 16 columns in a table. Oracle famously only lets you have 1,000 because somebody hard-coded it, right? It used to be like 200, and then they spent a year trying to fix it to go to 1,000. But that was 10 years ago. No one's going to change it again. Like it's like stupid things like that. But yeah, you're very unlikely to run out of space for this. There's other tricks to do if you get around this. Like in case of Postgres, you can partition a table. It's like here's a parent table, and then within that I have like subtables. So logically, it looks like a single table, but each one has their own. Right? There's ways to get around it. Say it again. The question is, for a row store database system, would it make sense to have 1,000 columns? People do it. Sure, why not? All right. There's easily applications that have 1,000 columns. Yeah. Enterprise stuff is nasty. Like anything from like the SAP Enterprise Resource, or the ERP thing, the thing they make a lot of money on, that thing is insane. Right? Because think of like an application running for like 30 years. Every 2 years, someone's got to add like 10 columns because something gets else added. Then before you know it, you're at 1,000 easily. To your point, I mean, like it's a long tail, right? There's going to be most tables are going to have maybe, I don't know, 20, 30 columns. But there's easily stuff out there that'll have that many. The same is, at that point, you would have a single row across multiple pages. Depends on what the columns are. So assuming that there are multiple pages? Sure, but the data system can handle that. Yeah. For our discussion here, we've simplified it and say, like, we assume it's all going to sit in a single page. But actually, no, we talked about large data record or large attributes. Now you just have a pointer to something else, to another page. And then at runtime, the data system knows how to stitch it back together. All right, so in this tuple-oriented storage, reads are pretty simple. All right. If I want to get an existing tuple, then I'm going to get its record ID. I'm not saying how to get that just yet, but assume there's some index. There's something that's going to tell me I want your email for your email address. Here's the record ID that has your student record. There's something there. It's the index that's going to tell us how to find that. But for our purposes right here, we don't care. So again, how do we find this? We go look in the page directory, go get find the location of the page we want, retrieve that page we want from that location on disk if it's not already in memory, and then now we use the record ID's offset that's embedded inside it to jump inside the page within the slot array to find the data we're looking for. right? Reads are pretty simple. In this case here, we have to do the lookup in the index to find the data that we're looking for. So we kind of do a lookup in this index. That's going to tell us for a given logical key, like your email address, when we look at the index, it's going to come back and say, here's the record ID. Then we do a lookup to go find the data that we want, given that record ID within the page. But what if we didn't have to do that? What if we didn't have to do a separate lookup in the index and a separate lookup in the table heap? So this is called index organized storage. And the basic idea is that we're going to use the index as the storage for the table itself. So again, what is index doing for us? It's a mapping from a key to a value. In this case here would be a logical key, like your email address, assuming like the primary key or something, and then the value is going to be the record ID, if it was a two-pointed storage. With index organized storage, in the leaf nodes, instead of storing a record ID, we're just going to store the tuple itself. So again, I'm not telling you what data structure this is going to be, but typically it's going to be a B+ tree. Could be a skip list, could be a trie, could be whatever your favorite tree data structure you want. So then now within the pages, the leaf nodes, it's going to look a lot like the slot array from the tuple-oriented storage. But in the beginning, the header, we're going to have this key to offset array mapping that we have to keep in sorted order based on the key. And these are just going to, again, be offsets within the page that gives us the tuple that we want. So now when I do that lookup based on your email address, I would scan down through the inner nodes in the data structure, land on a leaf node, then do a binary search inside this key offset array, and then that'll find the record that you're looking for. And I don't have to do that separate lookup in like the page directory to go find your tuple for given a record ID. Everything's right there in the leaf node. So SQLite famously, or SQLite and MySQL with InnoDB famously give you this to you. Like that's basically how they organize. It is how they organize the data in their system. With Oracle and SQL Server, by default, you get the slotted page architecture that I said before. But when you create a table, you can tell it, I want to do index organized storage. All right, so they'll support this as well. And just like before, the key offset goes one way and the tuple goes another way. Okay, well, so that solves the problem we had in reads before, where I wanted to do I want to find a record or a tuple based on the record ID. I have to go look in the index, and I then have to find for given key, look up the index, and the index tells me the record ID, and from the record ID, I can go get the page that has the tuple data. But we still have to worry about writes. So to do an insert, it's pretty straightforward, right? We just go check the page directory to see whether there's a free page for us that has enough space, or if there's a page that has enough free space for the tuple we want to store. Again, we know the size of the data we're storing because SQL is declarative. We know exactly what you're telling us to store, so we can figure out at the moment you try to insert it how much space we need. Then we go retrieve that page from disk if it's not already in memory, and go check the slot array to find a free slot and insert into it. Right? Ignoring the index organized storage, rebalancing the tree, we'll worry about that later. So inserting is pretty straightforward. And say we run out of pages, there's no free space in the current pages we have, we just allocate a new page and then insert our record in there. No problem. But now if we want to update a tuple, go through the same process before, go find its page from its record ID, go see whether the page exists. Then, assuming we're going to overwrite the data, which is not always the case in most systems, but assuming we are, then I'm going to go check to see whether the size of the tuple, the new value of the tuple that I'm trying to insert or update, if it's larger than the original value, do I have any space in my page? Now, because with the slotted array, I can reorganize things or try to free up space within the page. And if I can do that and I can get in the same page, great, I'm done. But if there's no space in the current page that I have, where the tuple currently exists, then I basically have to treat that as a delete, removing the original tuple, followed by an insert with the new tuple. And that's expensive, right? So tuple-oriented storage is really great for reads because, again, it's really easy to go find the thing that I'm looking for. For inserts, not so bad either, right? Because I can just insert a page over and over again. But for updates, they can be actually quite expensive, right? So part of the problem is we're going to have is that there's going to be fragmentation, right? Because we can't guarantee that we're going to be able to fully utilize every single page. Right? There's that little space in the middle where the slot array goes one way and the tuple data goes one way. And if I don't exactly line up perfectly, which is, you almost never do, then you're going to have a little space in the middle that's just wasted. Then now, anytime I want to go update a tuple, I got to go fetch that page into memory in order just to update one tuple inside of it. Right? Depending on the page size, if my pages are really large, then I might be really reading 16 kilobytes to go update a 5 byte value or 8 byte value, like something really small. So there's a lot of wasted I/O potentially, depending on what my workload is, what my data looks like. The other problem is going to be is that because now tuples can be stored across multiple pages, that means if I want to update a batch of tuples at the same time, I may have to go fetch all those individual pages, bring them into memory, and then update them. Right? If I had 10 tuples across 10 different pages, I have to bring in those 10 pages into memory before I can update anything. And then lastly, this is not so much an issue with tuple-oriented storage, but it's a way to think about how to design systems. Is that, well, what if we actually can't do any in-place updates in our non-volatile storage? Right? I can't bring a page into memory, jump to some offset within it, and then write out a new values to that at that offset. All right, there's some storage systems that actually don't let you do this. The Hadoop file system is one, probably one of the earliest ones that did this. Google has their own internal file system called Colossus. If you ever use Amazon S3 or other object stores, some of them provide these semantics. So you can't do in-place updates. You can only do appends. You can only create new data. You can't overwrite existing ones. If you want to get rid of the old stuff, you got to actually, it's a delete. And then you do more appends. So because of this, these issues, there's a different way to store data called log structured storage. Sometimes these are called log structure merge trees or LSMs. And the idea here is that instead of storing tuples in pages and then updating them in place, again, multi-versioning we'll cover later. That what I'm saying is not exactly true for multi-versioning, but what we're talking about today is going to look like multi-versioning, but not in the way that we'll talk about later for currency control. But the high-level idea is still the same. That instead of allowing it to do in-place updates, the only thing we can do is append new records to data pages. And the idea is that because now we're going to only do appends, of course we have to handle deletes, remove things, then that makes some of the algorithms to go read and write data more efficient or less efficient, but it's going to make our updates be really go really fast. Inserts go really fast as well, because you're just appending new records, and then that's that thing we talked about before, where we want to be able to minimize the amount of disk random I/O in exchange for more sequential I/O. Because so now if we only do appends, that's all sequential I/O. And that's going to be much faster for us. So the LSMs are an old idea. Goes back to 1996. Actually, the guy that invented the LRUK stuff we talked about last class also was the inventor of this stuff, the LSMs. The paper came out in 96. There was earlier work done on log structured file systems in the late 80s, early 90s, right? And so this is a successor to that in the file system world, but applying to databases. So there's essentially going to be two main data structures in a log structured storage system. There'll be a mem table, sort of in-memory data structure, where we do all our writes and make all our changes. And that one, because it's in memory, we can make in-place updates. And then as this mem table gets too big, then we're going to write it out to this immutable file called an SS table. I think it stands for sorted string table, or sometimes static or sorted static table, whatever. It's the same idea, but it's going to be a sort of compact form of what the mem table is that's going to have the changes that are made to the database. So there's only two operations to modify a log structure system. So we put where you add a new entry and delete. Right, there's no overwrite, there's no update, there's no upserts. Right? Put's basically the same as insert, but it may not be. Your put would be physically putting a new record in, but logically it might be updating an existing one. We'll see what that looks like in a second. So again, now we bring out again the demarcation line between disk and memory. Again, we have our mem table up above. Again, some tree data structure that's going to record changes that we're going to make to the database. I'm not saying what the data structure is. Again, it could be a B+ tree. Skit lists are pretty common. It could be a trie. It doesn't matter. So say now my operation is I want to put a new value in for key 101. I'm not defining how I'm determining what key 101 is. You can think of it the same way we did that, like the row ID in SQLite, like a sequential counter, right, where the system is maintaining for every new record or every new record. You just add a new key. You increment a counter by 1. So I'm going to put this put into my mem table, and I'm going to basically add a new entry for it. Same thing now. I want to do a put for key 102, the new value of B1. I'll put that in my mem table as well. And then now, if I want to go back and modify key 101 again, now with the value A2, again, because the mem table is in memory by its name, I can do an in-place update inside of that. I actually don't need to record the history of the previous changes that were made. There's a separate log file we're not going to talk about in today's class, but basically, because this is in memory, if you crash, you could lose data. But basically, we are appending the puts to a separate file, and that'll get flushed before we say the transaction is committed. But for now, we can ignore that. Just be aware that we have a way to keep the mem table durable. Same thing if I do another put on key 103, right? I'll update the mem table and so forth. So at some point, the mem table is going to get full. Right? We're going to run out of space. Like you think a couple hundred megabytes or something like that. So at which point, we're going to take a scan on the leaf nodes of the mem table. Right? That's because that's all the entries of the actual values for the different keys that we have. And we're going to store that now into a different form of the SS table. Again, think of this just like almost like the write-ahead log of the log. Like here's all the changes that were made that this mem table recorded. So again, if I made multiple changes to a key, like I changed key 101 multiple times, because I'm doing in-place updates in the mem table, when I write out the SS table, I only see whatever the latest version of that was. So at this point, once it's in my SS table, it's been initialized with the data of the mem table, I'm storing the data within the lowest key to the highest key. So this is in a sorted order based on whatever the key that we want. I'm going to go ahead and write this out to disk, to non-volatile storage. Do a flush, make sure it's there. And then I'll just populate a new mem table. Just keep doing this over and over again, making new SS tables. And these are now going to be basically sorted now in timestamp order from newest to oldest. All right, within one file, it's sorted from key low to high. But with across multiple files, I'm going to sort them, keep track of them in newest to oldest order. Like you put the file name, have a timestamp, right? And the timestamp is always incrementing as things go forward. So I'm going to show one type of compaction. That's probably the most common one, but I'll show another one, and I'll go more detail what this compaction scheme looks like. But at some point, this level is going to get full. So then I actually want to combine SS tables that are in disk, the first level 0, and I'll combine them into a new SS table. And then I can blow away the old ones. And the idea is that as you keep going down, these things get bigger and bigger, right? And the idea is that I'm throwing away things that I don't need anymore, and I always try to have like whatever the latest version is at each level for a given key. Yes?
I don't understand why we want multiple levels. Like, why not always merge level 0 with level 1?
This question is why do we want multiple levels? Why not just merge level 0 within itself? Give me 2 slides. We'll come to that. Right. But so one to be better for reads, one to be better for writes. I'm not showing key ranges here, and that's why it's maybe confusing. Give me a few slides. Yes?
Is the compaction working off because I assume these are ID button operations, so you can just throw out older operations for the same key value? Is that where we're getting the space back from? Or?
Yes, and 2 slides, right? So his question is, and he's correct, like, is this compaction, are we throwing out operations for that we don't need anymore? Yes. So if I do a bunch of puts and then on a key, and then I delete that key, I don't need to keep the puts. I just need to know that I deleted it. Right. So you basically end up with sort of this tier structure like this, where you have big, longer SS tables at the bottom and progressively smaller ones as you go up. All right. So that's how we do puts and deletes. We need to handle reads now. So if I want to do a read, the key 101, the first thing I'm going to do is go check my mem table to see if I have any entries inside that, because the mem table is going to have the latest version or latest changes that were made to a key. So I go check my mem table. If it's in there, great. Take whatever the value is and return that back. I'm also not saying what the value is. I'm kind of being vague here, but it's typically going to be the tuple itself, right? Just in sort of serialized form. But if the key that I want is not in the mem table, then I now got to go check all these different SS tables at different levels. And that's going to suck now, because I got to go do a bunch of reads to go find some, basically a needle in a haystack. All right? So the way to deal with this is that you basically maintain what's called a summary table in memory that provides some additional metadata about what's actually in these files, right? So I could say, for a given key 101, I could check at, does this key even exist at the different levels? So I start at level 0, because again, the levels are going, depending on my compaction scheme, could be going forward at a time. It could be also going across keys. But like, I want to see what level has my key. And then if I know that the key exists maybe at this bottom level here, but it also exists in a higher level there, I always want to choose the higher one, because I know that one's more recent. So again, we're making this trade-off to make our writes go faster in exchange for slower reads, but we can add some additional data structures to make sure the reads aren't as bad. Wait, say it again? The question is the key filter a bloom filter, or what was the question? Question, like, what is the filter? It could be a range filter to say, like, within this range, this key doesn't exist or not, because that would handle range scans. It could be like a single key. Does this key exist in this level or not? And that would be a bloom filter lookup. So that could give you we'll talk about bloom filters in a few weeks. So like, that could give you a false positive. It might tell you the key exists in this lower level. Then you got to go actually look and check to see whether it's there or not. Yes?
Sorry, so the way I imagine it, the key would have to be down to the field level, right? Like tuple and like which field you're updating. Because like, let's say I want to update this field for ID 123.
Mm-hmm.
Then in my mem table, I only have information about the field I'm changing. But let's say there are many other fields in my database.
The statement is, again, this is why I was trying to be vague about what the value is. The statement is if I update a record, if it's a blind write, I don't need to look to see what it actually was. I just put a put and I'm done. If it's like update Andy's salary or Andy's age, where age equals current age plus 1, I got to go read whatever the original value was. Then I got to do an update. And then what do I'm actually putting in the mem table? In the case of RocksDB, I think or most systems, it's going to be the full tuple all over again.
But so my point is, like, let's say it's just a write. I don't care what it was before. I'm saying like Andy's age.
A blind write.
Yeah.
Yes.
So if I do that and later on I want to read your record, it's not enough to like find your age. I need to find everything, right? So like your record may appear in multiple SS table levels.
Yes. So his statement is, you're basically asking, is there a given record that has multiple attributes? Is that those attributes broken across multiple SS tables? No, you would always have the full tuple with all its attributes in the record that you're storing as part of the value in the mem table or an SS table.
So like there's no blind writes in the sense like internally you're going to fetch it.
A blind write would be like an insert. But to your point, like, yeah, so his point is like, you'd have to do a remodify, right? You'd always go fetch the tuple, then update it. Depends on like what the query is. If it's an update where if it's update where you're changing all the attributes, then yeah, you don't need to see what the original ones were. You just do an update in place. Yeah. Or not update in place. You could do an update without actually reading it. Other questions? All right, so again, what are we doing? It's a basic key value storage architecture, where again, the value is going to represent the contents of the tuple. If we do a delete, we don't actually need to go find the data that we want and actually delete it, which is kind of nice. Again, in a tuple-oriented architecture, on a slot of pages, I got to go fetch the page, then mark it as deleted. In this case here, if I have the key of the thing I want to delete, I just put a delete key record in my log in the mem table, and then I'm done with it. Then anybody else that comes along wants to read that tuple, we got to, it has to make sure that it sees that delete record, notifying it that the record no longer logically exists. Even though physically it might be and it's still a bunch of SS tables, we know we should ignore it if we try to go do a lookup on it. Yeah, sorry, yes.
Yeah, so when do the merges get performed during downtime?
The question is, when do merges get merged? Next slide. Okay. So at some point, I'm making all these SS tables, running about the disk, and if I delete a tuple, if I update a tuple like 1,000 times, then I delete it, I'm going to have 1,001 records corresponding to that one tuple, but I only really need the latest one. So there'll be this background process that gets triggered based on the size of the SS tables, based on the number of overlapping key ranges. We'll see that in the next slide. Like, there's a bunch of ways, a bunch of mechanisms to trigger when compaction should kick in. And again, there's this trade-off between doing background maintenance and actually just running queries. Remember we talked about the background writer or the page cleaner and the buffer pool? Like, we could have a thread run through our buffer pool manager, find our dirty pages, and start proactively writing them out so that they get marked clean and they can get evicted. But if I'm spending all my time doing that, then I'm going to slow down queries actually trying to do real work. So I could spend all my time doing compaction to clean up all these SS tables, but that's going to make query execution run slower. So there really isn't a good way there's not a sort of one-size-fits-all solution to determine when you should trigger a compaction. But things like RocksDB have a bunch of different policies. All right, so say in the most simple form, say I have two SS tables. I want to merge them. And in this case here, I'm assuming that the order of the two SS tables is from newest to oldest. So the one on all the way over here is the newest one. The one after that is older than that. So the way I'm going to do basically merge is the same way you're going to do sort merge. If you know that algorithm, we'll talk about that again in 2 weeks. There's a join algorithm on sort merge as well, right? You basically just have two cursors that start at the beginning of both these files. Again, I'm showing two SS tables. You could have multiple ones. Typically, you want to merge multiple ones at the same time, right? But for our illustration, it's just two. So now what's going to happen is I'm going to look at whatever the key is being referenced at wherever my cursor is pointing at. In this case here, the first cursor is looking at a delete on key 100. This guy has a put on key 101. It says 100 is less than 101. I know that there isn't going to be a reference to key 100 in this SS table. So therefore, I can just take whatever that record is and put it in my new SS table. And then I move that cursor down, but I keep the other cursor at the same location that it was pointing at before. So now at this point here, we have a put on key 101 in the first one, and then a put on key 101 as well in the second one. But since this SS table is newer than this one, we know we don't care about whatever that put was. We only care about the latest one. So we go ahead and ignore that put and put the first SS tables into the new one. Then same thing, both of their cursors move down. We have a put on key 102, another put on key 102 in both of them. I don't care about the second one. I only put the first one. Keep moving down. Now I have a put on key 103, but I also have a delete on key 103. Same thing, they're operating on they're doing some modification to the same key, but I only care about the latest one. So I go ahead and ignore the second one, put in the first one. The first cursor is done. So now I keep scanning along, and whatever comes after that, I know I want to copy into my new SS table, right? So I put the put for 104 there. That's basically what compaction is doing. Now the tricky thing is going to be, how do I organize multiple SS tables, and what am I how am I deciding what SS tables to merge? And we said the when it gets triggered based on a bunch of different policies. So what I showed before was an example called level compaction, where I'm going to maintain different levels of SS tables of different sizes. And the goal here is actually to have non-overlapping key ranges within our levels, except for level 0, because that's the special one where as mem tables get full, we convert them to SS tables, we just append them to disk. So in that case, they will have overlapping key ranges, but everything below that will not. So again, assuming the SS tables are going to go from newest to oldest, our first SS table we're going to write now is going to have key range from A to R, right? Some arbitrary letters. The next one is going to have key ranges from E to T. And then the third one here will have key ranges from B to Q. So at some point, I'm going to run out of space, or somebody gets triggered, says, I want to now do compaction on level 0. So I'm now going to make a new level, level 1, and I'm going to take these 3 SS tables, and I'm going to combine them into two larger SS tables. And I'll do the compaction I just showed in the previous slide, where I'll have a cursor go through each one and remove whatever the oldest entry is for a given key, and it'll only keep the latest one. So, but then in my new SS tables I'm going to generate, now I have non-overlapping keys within this level. So if I'm looking for key X, for example, if I have to look at level 0, I have to potentially look at all the SS tables to find key X. Well, actually, I wouldn't be in any of them, but like, say I'm looking for key Q. I would actually have to look at all three SS tables to find that given key, because each of them have that key could fit in each of their ranges. But now when I do a compaction down to the second level, or level 1, since now they're non-overlapping key ranges, if I need key Q, I know I only have to go look in the second SS table. It may not exist, and again, I can use a filter to tell me whether it's going to exist or not. But if it could exist, then I know I only need to look at one SS table. Yes?
Sorry, can you repeat, why do we have multiple tables in level 1? Like, why did we end up with 2?
Next question, why do we end up with multiple SS tables in level 2? It could be just one giant one. Basically, the size of the SS table is growing. Sorry, size of the SS table grows per level. And so the cumulative size of the SS tables above that I'm merging down may be larger than what I can fit into a single SS table. So I drew 2, but it could just be 1. I just want to show, too, that you would have these non-overlapping ranges. So once this is done, again, I can blow away all the SS tables at level 0 and keep doing the same thing, just keep adding more and more, right? Doing appends. And now I have different ranges. And at some point, I want to do a merge. And again, these are going to be overlapping ranges in level 0. But when I create SS tables in level 1, they have to be non-overlapping. So I may actually end up recreating all the files again. So read them all into memory using my buffer manager, and then write them all back out, because the keys that are in the level 0 might be in any of the files. I might have to go in any of the files. I may have to generate a bunch more files. So if I have like 10 gigabytes of data on level 1, I run compaction. I'm going to have to read 10 gigabytes in, and I might be writing out another 10 gigabytes. Yes? The question is the number of levels fixed? No, I can go forever. In practice, though, like I forget the default is in RocksDB. You just end up with like really big files at the bottom.
Like for any specific setup is fixed, is it a constant?
Question is for any set of what? Sorry, for like.
For example, you have this one VNS, like is the default settings like we have, for example, 10 levels, and then it's always going to be 10 levels, and not.
The question is for would you have a setting for a database system to say I'm going to have 10 levels in my compaction scheme, and then you always have 10 levels? No, the very beginning I could set this thing to have 10 levels, but right here at this point we only have 2. It grows. Yeah, so never exceed that. You just end up with really large SS tables. A lot of them are maybe at the lowest level.
So why is this good for read heavy workloads?
Question: why is this read heavy? Why is this better for read heavy workloads? Because when we see universal compaction next slide, if I want to go find a key at a lower level, I only have to look at the SS tables that where my key fits in that range. Again, if you go back just to when we only had level 0, like this is fresh from memory into disk. These are overlapping ranges. So if I want key Q, it can exist in the first one, the second one, or the third one. So I have to check all of them. Now in this case here, like it would be, since they're ordered based on time, if I see it in the first one, I know I don't care about the other two. But in the worst case, I have to scan all 3. Yep. Other questions?
So there is possibility that the same key can exist in like level 0 and level 1.
The question is, can the same key exist in level 0 and level 1? Yes.
But because like these tables are ordered from newest to oldest, so this does not impact the like search speed.
The question is, because at level 0, it's sorted by newest to oldest, it does not impact the search speed. That meaning like, well, no. So if I'm only at level 0, and I want key Q, if it's not in the first one, I got to check the second one. So that's slow. If it's not in the second one, I got to check the third one. That's slow. Right? So in worst case scenario, I have to check everything at level 0. The summary table helps to maybe not do lookups on tables or SS tables that aren't going to have the data that I want. But in the worst case, I may have to check. So yeah, so reads will get slower. But that's why they have the additional levels, because now when I start compacting, going down the levels, I can guarantee that, again, for key Q, it's only going to exist in one SS table at level 1. Likewise, if I keep adding more, same thing. Q can only exist in one SS table. Whereas if it was just me just writing SS tables straight from memory, like I do in level 0, it could be in any of them. Again, and I just do the same thing. I do compaction down to this level, and I can blow away things here. Again, and now I have, again, non-overlapping ranges within as they exist now. But again, as I add more things, there may be overlapping.
At what point do we choose to compact it based on frequency? Every 5 seconds we do a compaction, or it's like if a particular table is this amount of memory we compact it?
The question is similar to the one they asked before. Like, what triggers compaction? Depends on the system. Depends how you set it up. So it could be that if I have a max size of all the files within a level, when that exceeds something, then that triggers compaction.
Why didn't we merge explicit memory, or like why didn't we merge the entire level up?
Say it again?
In this particular example, why didn't we merge the entire level 1 into a single level 2?
The question is, like, why did I do for this one here? Why did I merge it?
From level 1 to level 2, why did you only merge 2 tables and not all?
All right. Question is, why did I merge, in this case here, why did I merge only 2 SS tables from level 1 down to level 2? It's just the example, right? What's that?
Just on system setup, it would merge all 3 potentially.
Yeah, it's like you would merge more than 2. Right? I'm trying to make this work on PowerPoint, so like for simplicity, yeah, you can be very, but it's going back and forth, you can be very aggressive and try to merge everything, but like that's going to be, you're just spending your time doing compaction, not running queries. All right, so let me show universal compaction real quickly. Universal compaction only has one level. And again, it's the SS tables as they exist, as they're being written out, but from the mem table in memory to disk. So we want to do compaction on them, but again, we don't want to maintain multiple levels because we don't have this write for amplification problem where every single time we want to do compaction, we got to read a bunch of things in and then write it all back out. So instead, we're going to be more targeted compactions. So in this case here, like I say, I'm going to take these 3 SS tables. Again, they all have sort of non-overlapping key ranges, but they're ordered through time. And then now I'm going to take these 3 and merge them into a single SS table, compact them, and reclaim the space. And I can do this again for the next 2 here, compact them, and put them into a larger one. So this is great for workloads where you're inserting data very quickly, do a lot of updates. It's great for workloads where I typically only want the latest data that I just inserted. Like if I'm inserting time series information, like the temperature of this room, I only care about the last 5 minutes, 10 minutes. I don't care about what the temperature was a year ago. And so in that case, I'll be able to look up very quickly and find the data that I want in the newest SS tables that are on disk. Right? Classic trade-off in computer science of like, I'm spending more time, more energy to make the, when I write things, to make the writes more expensive, but my reads will be faster in exchange for, or as opposed to making my writes go really fast, but my reads a little bit slower. Right? So this is making the writes go faster, but the reads could potentially be slower based on what you're looking up. Okay, so to finish up, log structure storage in the last 15 years has become super common. And part of this is because of RocksDB. RocksDB is a log structure merge tree key value store that actually supports both these compaction schemes. You can set whatever you want. I think default is level compaction. But that has been used as the starting point for, or the built-in storage manager for many new systems. RocksDB was created by Facebook or Meta, whatever it is now, but they weren't the original authors of it. It's actually a fork of something called LevelDB that came out of Google. This is built by Jeff Dean and the people working on Bigtable. They built this log structure storage embedded key value store called LevelDB. Facebook forked that and made RocksDB. What's the first thing Facebook did when they forked LevelDB to RocksDB? What was that? No, not copyrighted. No. I think it was Apache license maybe, so it wasn't an issue. Non-legal thing. What's the first technical thing they did? No, that's a legal thing. He said change the license. No, technical. They changed the code in what way? What did they do? Removed mmap. Right? That's the very first thing they did was get rid of mmap because it's garbage and switch to a bufferable manager the same way that we talked about last class. Right? And like I said, a bunch of the different systems, you start off using RocksDB as their own internal storage manager. Cockroach did this, and then over time they rewrite it. This is, again, a small smattering of log structure storage systems. There's a lot more. And as we said, the challenge of this approach is it's going to be really great for doing writes, but the compaction is expensive, and we may have this write amplification issue where we do one update to a single tuple, and even though we never update it to ever again, we're going to read it in, write it out, read it in, write it out over and over again multiple times because of the compaction process. Whereas like in a tuple-oriented architecture, if I write something to a page, it gets written out to disk. I never I never read it again. I never write it out over and over again. Yes?
So does this mean that all those DBMS are like bad for read-heavy workloads?
Question is, are all these DBMS bad for read-heavy workloads? No, like things like ClickHouse will be really, really good for it.
So
because
log-based storage is not necessarily bad for write-heavy workloads.
There's a bunch of extra stuff you can do to mitigate the issues. Then that'll be next class. Okay, so next class, again, we're actually going to break your preconceived notion of what a database looks like. For now, we've been talking about these rows that are just contiguously in disk or in memory. We're going to flip that and talk about column stores. We actually store data as columns, not rows. So that'll be next class. For project one, I'm going to quickly go over this before we jump to the speaker. So this has been posted on Piazza, and the code is on GitHub. Right, you're going to build your own bufferable manager in the bus tub system. So you're going to build a replacement policy algorithm based on ARC. Again, we'll have a recitation next week that goes over the algorithm in more detail, but it's pretty straightforward. Then you build a disk scheduler and then a buffer pool instance. And that'll be due on September 29th. So the replacement policy is just the algorithm itself that actually decides what to evict when you need a page. You're allowed to use the built-in STL containers for the ghost lists and the most frequently used, most recently used lists. So you don't need to build your own separate vector indexes and things like that inside your, not vector indexes, your vectors or lists inside C++. Just use the STL ones. Because it's in memory, right? The buffer pools in memory, we don't care if we lose the data, well, what's in these lists if we crash, right? It's okay to use the built-in data structures. For the disk scheduler, you're basically going to support asynchronous I/O through SDO, SED promise callbacks. And the basic idea is that other parts of the system are going to ask the disk scheduler, hey, I want this page. And then it's going to be, you're going to build the piece of the system that's responsible for scheduling the reads, fetching those into memory, and then handing them off to the buffer manager. All right. You're going to put this all together and now actually build the frame storage and the buffer manager and the page table that actually takes the requests for the pages from other parts of the system, goes to the disk scheduler, tries to find the pages you want, brings it into memory, and then if you don't have any space, it runs your arc replacement algorithm to decide how to remove things. Okay? So super important. Don't change any file other than the ones we tell you to change, because when it runs on Gradescope, it wipes away whatever you give us for anything else but those files. And if you make any changes in there, it won't run. And then the projects are all cumulative. Right? So project 1 is the first start into this, but 2, 3, and 4 will be based on your buffer pool implementation for this project. So we want to make sure that we have a bunch of tests to make sure you don't screw things up, but you don't want to fall behind, because if you're trying to fix your buffer pool manager 2 months from now, it's going to make all the other projects a lot harder. If you have questions, please come post on Piazza or come to office hours, but we won't sit there with the GDB and tell you how to debug things, right? We assume you know how to do that in C++ because of Project 0. Just like in Project 0, do a bunch of checks to make sure that your code looks good. And then for extra credit this year, we will have a leaderboard. So we have a version of BusTub that runs on Gradescope, and whoever has the fastest buffer pool implementation, actually for all the projects going forward, will have a ranked order on the leaderboard, and the top 20 gets extra credit. And then this year, we're actually going to try to get a trophy made, like the Stanley Cup, or not that big, but like whoever has the highest leaderboard scores, and at the end of the semester, we'll put your name and year at the bottom of it. And that way, over the years, we can get this thing and start growing it. Okay? Don't plagiarize, because you'll get it messed up. And then ask questions. All right, so let me jump to the speaker. Oh, all right. This is Joseph. He's been at SingleStore for a while. You're coming next week as well, right?
I'm going to be here next week, yeah.
Right. He's awesome. He's super smart. He's gonna come next week. The floor is yours, man. Go for it.
All right, cool. So yeah, I'm going to tell you guys a little bit about SingleStore. SingleStore is kind of a unique database in the industry. I think it's probably one of the most unique databases in the industry. And so let's just dive right in. So this can be kind of a rapid fire talk. So I'm going to talk a little bit about the 2 types of database workloads and how SingleStore presents itself as a sort of hybrid option. And I'm going to switch gears completely and talk about modern cloud systems and the kind of benefit SingleStore gets from running in the cloud. So let's get started. So the 2 types of database workloads. So you've maybe seen this in your class so far, or you will later in the semester, but there's basically 2 broad categories of database workloads. The first is OLTP, online transaction processing. So it's characterized by a large number of transactions, super high concurrency, small reads and writes, stuff like that. And so it's like, any row you need to be able to fetch at any given moment. And you might need to be able to update it at any given moment. So everything is kind of optimized to be able to find stuff, index stuff, do transactions, change things around. And so you typically will have very high concurrency, lots of queries that are small, hitting the database all at once, very short SLAs. You expect things to return in milliseconds, and you really care about ACID. You really care about your transactions being atomic and not seeing any weird side effects of isolation, and you don't want your rights to be lost. So you care about these kinds of things with that kind of workload. So you can think about running applications. You can think about like running literal transactions at a bank, or if I click on something on my website and it says you pay me and I'm going to send you this thing that you just bought. And so typically these kind of databases will use row-oriented data structure, right? Because every row has to be findable and updatable very fast. So they'll typically use B trees and skip lists, which allow you to find one row very fast. And you've probably learned about that in this class. So examples of this, Postgres is basically synonymous with OLTP these days. Older databases, Oracle and SQL Server are, of course, there. Cockroach, Spanner, these things being the kind of modern, large-scale transactional databases. The other type of database broad category is analytical databases, OLAP databases. So these are characterized by large bulk processing queries. And sometimes the queries will take minutes, hours, or even days to run. Maybe these days that's not considered acceptable, but these large reporting queries can take a long time. And you will often run on huge scales of data. Terabytes or petabytes are not uncommon. So you should think large reporting queries, analytics, dashboards, your loads are big bulk loads that you do periodically. You're not updating one row. And so the data structures used to build these kinds of things are very different. You do these column-oriented data structures. And you're going to learn about that in this class, I assume, I hope. I love column stores. I think they're so cool. And they're one of these data structures that just makes me so happy. So it's going to be fun to learn about those. But yeah, so they use these column-oriented data structures that are really, really good at scanning really fast. Really, really fast. And so examples of this kind of database are Snowflake, ClickHouse, Redshift, BigQuery, Vertica. There's different flavors within this thing, but they're all pretty much distributed column store systems, and they're good at big data analytics. So the question is, why are they hard to do both? And like, why are there these two different data structures and I can't just have one data structure that does both? And so, you could talk about like, oh, row stores will cause, write amplification and you're doing a bunch of random IO. And so their scan speed is limited. And that's like kind of true. But really the reason is that column stores are really, really, really fast. So when column stores do scans, they just, they just blow through your data. And it's really impressive and it's a really cool technology. But column stores the updates are generally not fast. So if you want to scan huge amounts of data, you're kind of forced into this column store world, and your updates will suck because of it. The questions of what other data structures do are almost irrelevant. The column store is just so good. There's a fundamental fact of the universe. No column store will ever be as fast as row store on point queries. And so like if you have a database, it's either a column store for analytics or a row store for transactional workloads, and typically it's not both. But that's what SingleStore is. It's a hybrid row store, column store thingy. So what is SingleStore? What is SingleStore as a hybrid option? Why do we exist? We're not really a hybrid option. It would not be fair to say that we're some kind of Franken thing. We're a column store with tricks, is what we are. We're a column store with a row store bolted onto it that is kind of considered the first segment of that column store, and it's used to store the hot rows. And then we optimize our column stores in a way that don't negatively affect the scan performance, but make it so that they're decent. Not as good as row store, but decent at transactional workloads. And the way we do that is, first of all, you change the column store encoding so that they're seekable, which by itself doesn't give you much, but you add these secondary hash indexes that tell you the offsets. And so it's like, oh, I know all the offsets, I can seek in real fast. And you kind of use that row store to kind of manage the locking virtual locks for the stuff in the column store. And I don't have a ton of time. I could give an hour presentation on each of these things, but somehow it's a column store that doesn't fall over when you try to do transactional stuff. And that is very unique in the industry. And And yeah, so the column stores are not generally good at concurrent writes, but this one is. And for those things that really need transactional workloads, we do offer dedicated in-memory row store tables as well. We used to be called MemSQL. We used to be mostly focused on that in-memory row store thing. That we changed our name because we're not really mostly focused on that anymore. But we do still have those. What does this buy us? What kind of workloads can we do that other competitors can't? Well, analytical databases love these analytical benchmarks, TPCH, TPCDS, there's a ton of them. And these analytical benchmarks, they kind of have the flavor of, they'll give you 100 queries or whatever, and, Snowflake's better on one, BigQuery's better on a different one, ClickHouse is better on another one, SingleStore is better on one. And it's just like, it's a bag of tricks. It depends on, does your optimizer have this thing? Does your query execution have this thing? Does your column store execution have this thing? And so SingleStore is competitive with the best, data warehouses on these analytical benchmarks. OLTP databases do not finish these. If you're not column store, you don't stand a chance. Don't even bother. So SingleStore can do these things, and we're just as good as anyone else. But we can also do the transactional benchmarks. We can do TPCC, and we can do other sorts of point right workloads, and Snowflake it doesn't work. It just doesn't work. So we're the only. It's not about being better than anyone else. It's like we're the only one that can actually finish all of these, and that's very cool. So we're the only system that I'm aware of that can finish all three, at least the only commercially available one. I think that there's some academic ones that can do it as well. And that's pretty cool. So are we a hybrid database? Maybe our marketing will tell you we're HTAP or something, but I think of us as an analytical database that doesn't fall under high concurrency or point workloads. We can do a wide variety of mixed workloads like dashboards, logistics, manufacturing, streaming AI, that kind of stuff. And it's mostly analytical with enough transaction processing that other systems can't keep up. Cool. So I'm flying through this. I got a couple more slides that are on a completely different topic of modern cloud systems, but maybe I'm also over time already. So maybe I should stop for questions and just let that be the presentation.
Yes. Any questions for Joe? Yes.
So using worse encoding would mean higher storage requirements, right?
His question is, would using worse encoding means higher storage requirements? Yes.
I couldn't take that.
Yeah. The question is, he's asking about encodings. Let's hold your question next class. Joe's his setup is basically the intro for next lecture. This is fantastic. So a bunch of stuff may not make sense now. It'll make sense on Monday. And plus he's coming to campus and you talk to him again about it. Okay? All right, guys, let's thank Joe. And like I said, DJ Cash's radio show is this Sunday at 1 o'clock. And then see everyone at the visit day on Monday. Hit it.
Acrobats over tracks. Cash money, flick flips, acrobats over tracks. Cash money, flick flips, acrobats over tracks. Cash money, flick flips, acrobats over tracks. Get the fortune, motherfucker fan. Maintain but never strain, flow with the grain. Get the fortune, motherfucker fan. Maintain but never strain, flow with the grain.